Hello, I'm Mr. McBrien, and this is Robotics Club Certification 4, Circuit Schematics. Today, I'd like to talk a little bit about additional tools for interpreting the schematics that others have created, and some discussion about creating good schematics that match accepted processes. So, we might ask ourselves, in the context of a large world and many languages, how we're going to communicate our electronics designs accurately. In the end, devices are rarely created by a single person. Often they're not created by even a single group in a single geographic location. For this reason, communication is very important. And a simple text-based description isn't really effective when we think that a circuit is a three-dimensional system. We need pictures to be able to represent circuits. And in order to make these pictures be effective, we need to establish some boundaries, some accepted systems that mean that other people on the other side of the world, who we may never have met, can interpret our schematics accurately. Okay. Why is this important? Well, if we want to submit a patent, we have to have an accurate schematic or our patent may not be valid. We want to be able to communicate with coworkers down the hall or across the globe. And we want to be able to, especially when we hand off a design to another person to build it, we want them to be able to create accurate prototypes without the need for a lot of back and forth discussion. So, to turn it on its side, if we have a bad schematic, it can be very inconvenient. It can cost weeks or months in a project. But, if a bad prototype is created from what is a good idea, it could be dangerous. Okay, so the basic layout of schematics, we've already taken that as a given. Lines represent wires. Now, dots represent conductive joints. Intersections on the screen, on the piece of paper, may not necessarily be connections, unless it's the only option. So this is sort of one of our default circuits, a very simple circuit with only a few components. We can see the connections here are obvious, not because there are dots connecting them. Actually, if you look closely, there are small dots, but those don't need to be there. The reason why is because that's the only path that the electrons could take. So we take that as a given. Now, another more complicated diagram then has, yes, it has dots to show electrical connections, but the lines cross here, and this will not be interpreted as a connection by a reviewer. And so that's an important distinction to make. Sometimes we'll see a little hill to represent that they don't connect, but in general, those are not connections. Put a dot there if you want someone to interpret it as a connection. We've seen our symbols before. All of these could be important for our robots, but I'll highlight a couple. The resistor, of course. We may need a light sensor at some point. Transistors are very useful in robotics. Of course, our power supply. We'll use LEDs when we start building circuits together. Switches, and a ground that represents the negative connection on a battery, regardless of where we place the ground. Okay, a quick reminder about the power supply. It's our source of potential. It's always going to be direct current for our robots, mainly because it's a battery. So if you see, interestingly, if you see a single cell, it's implied it's 1.5 volts. Usually you'll write the voltage beside the battery rather than counting out a whole bunch of cells. And it's important to note that while sometimes we'll see a plus on one end of the power supply, the larger bar shown here represents the positive side. So a plus is not a necessary convention. When we label the power source, if you're reading someone else's schematic, it may be labeled a lot of different ways, not just as that kind of battery symbol. So we may see a V with underscore CC. It may be labeled as positive voltage and maybe the value. Sometimes we'll just refer to it as hot. Sometimes there will be a red wire, even on the schematic, but definitely in our circuit. Note that in general, the circuits will have the power at the top of the page, so they have the positive potential at the top of the page. And so this one combines several of these concepts then. So we have a red portion of our circuit, and it's at the top, and of course we have our power supply labeled. Okay, the ground is the source of electrons. By convention, it's 0 volts. It's the negative terminal on the battery and the smaller pole of the battery symbol. And it also is sometimes shown like this, representing a wire going into the ground. So these, it's interesting to note, are totally equivalent circuit diagrams. So we have both of these going to ground. That's perfectly appropriate. And it's the same thing as if we had the LED shown connected into the battery. And usually by convention, the ground's at the bottom of the circuit. Okay, wires, we don't often talk about them, ironically. Lines on the schematic represent wires. These schematics generally have wires drawn vertically and horizontally, not diagonally, although there are exceptions. So we've seen over and over again these orthogonal wires, these running east-west and north-south. This is an acceptable circuit. This kind of goes away from conventions. And if our team submits a circuit that looks like this, a circuit diagram that looks like this, we're going to lose marks at skills competition. And it's just a bad habit to get into. Okay, current flow, we've talked about this a little bit already. It goes from positive to negative or from source to ground. We'll talk a bit about this in a few seconds, but in any simple circuit, current flows the same across any point. When I say simple circuit, a series circuit. The direction of current flow is the opposite direction for electron flow. And it might be inconvenient, but that's just life. Current goes from positive to negative. Electrons go the opposite direction. Okay, so if we want to, at skills, get as high as possible marks for our schematic, we're going to match our symbols as closely as possible if we're using a pencil or pen. We're going to be as tidy as we can and be sure to use a straight edge for wires. Okay, so we've got all these conventions we've talked about. Are they required? Is a schematic wrong if it breaks those rules? Well, generally, what we can say is no. When you follow those guidelines, a reviewer, an engineer who reviews our diagrams, can easily see really quickly what's going on. If we break any of those conventions, they're going to have to spend time looking at it. There can be times when we need to, just because a circuit's complicated and we need space on the page. But in general, we want to follow those rules. Okay, a little bit more about reading schematics then. We haven't talked too much about Kirchhoff, but his first law is kind of interesting. It's really just the law of conservation of energy. It states that the total current entering a junction is equal to the total current leaving the junction. Another way of looking at it, the algebraic sum of currents at any junction is 0. And we're going to talk for a few seconds about how we apply that concept to some simple problems. If we look at a battery, current out is going to be equal to current in. So if we look at our battery here, our current goes out to feed our various devices. The current has to come back into the battery. Electrons just don't go away. So the electrons have to come back to the battery. Similarly, resistors in series have the same kind of thing. Current in is equal to current out. Okay, so in this case, then, we have two resistors in series, and the current passes through both of the resistors, and they both have the same current. Resistors in parallel, on the other hand, we have to consider the nodes before and after those resistors in parallel. And so the overall current is distributed between these resistors. So in this case, we have a simple resistors in parallel circuit. We know that there's a sum of current leaving the battery, going through those resistors, and going back into the battery. And the only question then is, how is that current distributed between those resistors? Well, it follows Ohm's law. So if you're comfortable with Ohm's law, you can define it yourself. But we can say because the 5 ohm resistor has 1/4 as much resistance as the 20 ohm resistor, it gets 4 times as much current as the 20 ohm resistor. And if you think about that for a few seconds, you'll probably realize how that works. At any rate, Ohm's law applies to both resistors. Okay, for your homework then, please complete the circuit schematic worksheet and go ahead and do the online quiz, and then you can move on to Module 5. Thanks very much for your time.